So far in quantum mechanics, we saw what are operators, commutation relation, and expectation values. We also saw how a physical quantity is considered to be conserved. Now in this video, we'll talk about the Ehrenfest theorem. So the Ehrenfest theorem is given by this general equation, which calculates the change of the expectation value of an operator A with respect to time. So first of all, let's try to derive this relation. For an operator a cap, its expectation value in the state psi can be written as this expression. Now, by taking the time derivative of this expression, we get this expression. Now, expanding the derivative gives us this expression. We can substitute the first and the third expression using the time dependent Schrodinger equation given as, and by taking its Hermitian conjugate we get this expression. Since our Hamiltonian is Hermitian, which implies h dagger will be equal to h in this expression. Now by substituting these values for the first and the third term, we get, now taking 1 by I h cat common, we get this expression. For the first term, we have the commutation relation of a and h. Therefore, our expression will become this in the final state. Now, for any quantity, its expectation value is written as this expression in terms of the given state psi. So, this expression can be also written in terms of this notation, which will give us finally this expression. And hence, this looks like a general expression for the Ehrenfest theorem. Now let's take two special cases for a position operator and momentum operator x cap and px cap, and here we are only dealing in one dimension. So in case of x cap and px cap, these operators do not change with time. Since an operator corresponds to making a measurement, and how we make a measurement of position and momentum do not change with time. Although the result of the measurement may change with time, that is, we can get different result if we measure our system at different time. But the process of measurement, that is the operators, do not depend on time. On this note, we can write the expectation value of a partial derivative of x cap and the expectation value of a partial derivative of px cap equal to 0. So now let's write this general equation for x cap and later for px cap. The Ehrenfest equation for a position operator x cap is given by this equation, and since dou x by dou t expectation value is 0, we can neglect this term. Now let's take our one dimension Hamiltonian for kinetic energy px square by 2m and scalar potential v of x, and putting this value of our Hamiltonian in this commutation, our expression for x cap becomes this equation, and by expanding the commutation we get a scalar potential is a function of x, and we know the commutation relation between an operator and its function is 0, which implies this term would be 0. So we are only left this term, and we know x px square is equal to 2I h cut p of x. So putting this value here, our final expression for x cap becomes this expression, where we have cancelled I h cut from the denominator. Now let's similarly derive the Ehrenfest equation for our momentum operator. So writing the general equation in terms of p of x, we get this expression, and since we know this partial derivative expectation value is 0, so again neglecting this term, and by expanding the Hamiltonian we get this expression. Now let's solve the commutation relation. So by expanding this commutation relation we get this expression, and since these two p of x will commute, this term will be 0 and we are only left with this term. Therefore, this is the equation that we are left with. Now we will use the property of a function operator given as p of x with any function f of x can be written as minus I h cut derivative of that function f of x. This implies a v of x is also a function of x. Therefore, this expression can be written as p of x v of x equal to minus I h cut derivative of v of x, which can be given as the gradient of v of x. Now putting this value here, a final expression for p of x becomes this expression. Now we have derived the two Ehrenfest equation for our x cap and px cap. Now let's take m d square by dt square expectation value of x, which will be equal to m d by dt of expectation value of x. Now the time derivative of expectation value of x is given by the first equation for x cap, which is px by m. So putting that value here and cancelling m, we are left with the time derivative of expectation value of p of x, which is given by our second unfirst equation for p of x, which is equal to negative of the expectation value of gradient of v of x. So putting that value here, we get finally m d square by dt square expectation value of x equal to negative of expectation value of gradient of v of x. Now the above equation looks familiar to our classical equation, that is the Newton's second law, given by m d square x by dt square equal to f. And if this force is derived from a scalar potential, then this f will be equal to negative of gradient of that scalar potential v of x. That means by exploiting the Ehrenfest theorem, we may make a connection between quantum and classical particles. But how can we make this connection remains the question. So quantum mechanically we have this expression, and in classical mechanics we have this expression. And for this part to be equal to this term, that is m d square x by dt square expectation value of x cap to be equal to negative of gradient of v of x, the value of x should be equal to the expectation value of our x cap operator, which implies that expectation value of gradient of v of x is equal to gradient of v of x when x is equal to expectation value of x cap. This implies that the potential is evaluated at the center of the wave packet, which represents a particle in quantum mechanics, which then behaves like a center of mass of a particle, which is the abbreviation we use in classical mechanics. So now let's see how far this implication is true. Let's expand the scalar potential v of x in its power series, which will be given as summation n v of n x raised to n, and its gradient, that is v dash of x in its power series, would be given as summation n v n x raised to n minus 1. Similarly, the expectation value of the potential, that is v dash of x, can be expanded in its power series as summation n v n, since we are calculating the expectation value x cap n minus 1's expectation value. And from this expression we can write v dash of x when x is equal to expectation value of x cap. This expression would be summation n v n at x equal to x cap, so it would be x cap n minus 1. Now from this expression, for these two equations to be true, these two summation must be equal. That is x cap n minus 1's expectation value must be equal to expectation value of x cap raised to n minus 1. So let's check how far this is true. So expectation value of v dash x is equal to v dash x at x equal to expectation value of x only when x raised to n minus 1's expectation value is equal to x expectation value of n minus 1. And this equality is only true when n is lesser than true, that is when x cap 2 minus 1's expectation value is equal to x cap expectation value raised to 2 minus 1, which is nothing but x cap expectation value. And it would be not true when n is greater than 2, that is for n equal to 3. We can see that expectation value of x cap 3 minus 1 would be equal to expectation value of x cap square, and expectations value of x raised to 3 minus 1 is equal to expectation value of x raised to 2, and these two expressions are not equal. So we can conclude that our classical equation connecting with the quantum equation we got from the Ehrenfest theorem is true only if our potential is a polynomial of degree less than equal to 2. Therefore, our Ehrenfest theorem says that expectation values of physical observables follow classical equation of motion if the potential is given in terms of a polynomial of degree 2 or less. So for this to be equal to this, a scalar function v of x must be a polynomial of n lesser or equal to 2, which may implies that we may make a connection between the quantum and the classical equation. So this was the complete description of our Ehrenfest theorem. I hope you understood it.